Right. Yep. Okay, now,
You just need to eat the microphone.
eat it.
There you go.
It seems very loud. Is it too loud?
No.
It's not too loud, okay.
Perfect.
All right, so the electric grid strikes. So let's go back in history a little bit to our ancestors. These are San Bushmen. They get up early in the morning, they go out all day long into the desert and the bush, hunting, etc. So someone did a study where, so I'm gonna try this laser pointer. Larry, how do I make the laser pointer? Click up the top?
Nope. Nope.
Which one?
This one right here,
Okay,
the red one.
okay.
There.
So we have this blue line represents, this is the intensity, the brightness of light
Bring the microphone
over the
closer
day.
to the mic.
Over the day, this is the brightness of the light on this axis, and this is throughout the day, from the morning through the middle of the day. So our hunter-gatherer ancestors, probably very similar to the San Bushman tribesmen of today. What they do, they get up and they go outside with bright light, bright light, bright light. When it's really dark, they might seek some shade, but they are outside. Whoops. Sneak preview there. And then when the sunset comes, they're getting no other light. They're sitting around the fire socializing, going to bed. That is how our bodies evolved on planet Earth. Now, what modern humans are doing in America, we're getting up and we're going indoors and we're getting about this much light. And then all day long, we're indoors and we're getting this much light and this much light. Then at night, nothing much changes. We're still indoors and we're still getting about this much light. So this is would be considered a circadian mismatch. So this guy here, this is what he's doing, is he's getting the same low amount of light, and then we'll talk about what kind of light in a minute, throughout the day. So compared to our ancestors who spent most of their working hours outside, modern humans now spend 90 to 95% of their time indoors. So I can see already this is a problem. Tristan Scott, who's an interesting character online, he says our bodies are starved for photons. So it's not just the mismatched wavelengths of light, but it's just the sheer volume of light that we're used to, that we should be getting. Neolithic dwellings used oil lamps with whale oil and hearth fires. This is Scarabray from Scotland. In Rome, they had natural light with these beautiful atrium openings, and they used fancier oil lamps. In America and Europe, before electricity, we used to light our homes with candles, oil lamps, firelight, of course. Then gas lights came in around, I think in the late 1700s, 1800s. Kerosene lamps, these were all of the ways that we lit our homes. Families would gather at night by the hearth. They would do work, spinning, they would knit, they would whatever. But then, in 1879, Thomas Edison invented the light bulb. And it was a sensation, and by the 1890s, most of the urban areas had been electrified, and then by the 1930s, it had spread to most of the rural areas. Okay, so let's look at the spectrum of lights. So for years and years, we're using these oil lamps, firelights, whatever. They almost all had this same type of spectrum. Very little blue, and then a whole lot of red and infrared. Candles are that way. Now, when Thomas Edison invented his light bulb, the incandescent light bulb, the spectrum was very similar. So it really wasn't that big of a difference at that point in terms of what we were being exposed to at night and what it had been. But if any of you remember the energy crisis of the 1970s, then suddenly everyone became panicked about we have to reduce our energy usage. So compact fluorescent bulbs, we always had the fluorescent, long bulbs, but the compact fluorescent bulbs were pushed by government, and everyone's like, we've got to save energy. So look at the difference. Whoops, sorry about that. Am I going? Here we go. So look at this spectrum of light. It's completely different. It's got a lot of blue, it's much brighter, and the infrared and red are completely eliminated, and that was the idea, because that's where all the heat is so-called wasted. So they wanted to get rid of those infrared and red wavelengths. So there was lots of blue light, very little red or infrared. Then, around the year 2000, LEDs became popular, and they were way more energy efficient even than compact fluorescents. And they were even stronger in the blue ranges of light. So each time a new light form is invented, the spectrum is diverging more and more from what our ancestral light sources had been. Nowadays, in almost every building, you'll see these ceiling panels. They're in my office building. They are LED light panels, so they have that spectrum of light. And how many people find that type of light disturbing or unpleasant? Yeah. LEDs are used in our devices, they're in our TVs, they're in our computers, they're in our smartphones, our tablets, flat screen TVs. So the scientist Scott Zimmerman says, in our arrogance, we thought we could just throw away something our body's been using for millions of years and has adapted to and not have a consequence. John Ott, quote, "Malillumination is to light as malnutrition is to food." Okay, so let's talk about the famous bad guy blue light. So blue light is not bad. It wakes us up in the morning and we, keeps us going throughout the day. What is bad is narrow band blue light that is not integrated with the ranges of red and near infrared and ultraviolet and all of the natural symphony of light that we would be getting from the sun. And this is a paper about how blue light suppresses melatonin. Now, blue wavelengths of light strongly affect our body clocks. Blue light at night confuses our biological clocks. They're basically telling your body, okay, it's daytime, be awake. So if you look at your devices at night and you have trouble falling asleep, this is why. So don't do that. Another thing blue light does is it seems to activate the dopamine reward system in the brain that makes you addicted. So we've got two different negative whammies on our body systems based on being, looking at our devices too much. In Las Vegas, they use flashing lights with at the slot machines to keep people engaged, and that creates a constant dopamine release, and that is addictive. And look at our poor younger people completely caught up in this blue light addiction. And here's a few studies that back this up. I'll just move quickly through these. It affects vision, it affects cognitive function. Mental health problems in young people have increased in correlation to the amount of their screen activity. Okay, this is my section, right? Okay, now this is the big question. So when we told our friends, we're doing this, this talk on how natural sunlight is good for you, several people's like, oh, I can't be in the sun because I've had melanoma, I've had skin cancer. So we wanted to talk about, is UV light inherently dangerous? Because everyone is completely convinced that it is. So in order to contradict this is a huge study that studied 30,000 women in Sweden over a 20-year period and gathered all kinds of data on their health issues. So this study was, in theory, supposed to kind of prove once and for all, more sunlight you get, more cancer you get. But in fact, it proved the exact opposite. So the more sunlight that these women received, the lower all-cause mortality they had. And the women in the lowest quintile, the lowest 20%, had double the risk of poor health compared to the group of women who had the highest in exposure. And here's another study that points out that people who work outdoors all the time do not have a higher risk of skin cancer than people who do not. So I would say that kind of lays to rest the idea that in general, sunlight is bad, it's dangerous, you have to use sunscreen all the time. It's like, not really. So how can we get sun safely? So sunlight tolerance is earned through progressive overload. You gradually increase the demand placed on your body to grow stronger over time, kind of like when you weightlift. You start off with a little bit, it stresses the muscle fibers, they grow in response. In the same way, to tan safely, you need to slowly increase. The other thing you need to know is, what is your skin type? If you have that very pale, freckled skin and red hair, etc., you have to, you live in Colorado, you are in a mismatched relationship to your environment that your ancestors evolved. So you have to be really careful. So hormesis is the concept of a controlled stress that triggers an adaptive and regenerative response. So for UV light, tanning, which is the skin's production of melanin, that's what makes you tan, that's the adaptive response. So that's, in order to develop, some people would call that a solar callus, just a basis that you can slowly build, is start with early morning sunbathing. At the low angle, there'll be very little UV, as Michael showed you in that previous slide of how the mixture of lights change throughout the day. So you can slowly get your body used to it, and you'll be getting all of this infrared light, which is very healthy for you. If you're super pale, you're really worried, just start with your feet, and then kind of inch up to your legs, arms, and then eventually expose your torso. If you can get it on your stomach and your breasts, if you're a woman, then I think that's a good thing. And then you just slowly ramp it up. Just a very common sense approach. Train your melanin system, your tanning system, to respond gradually, without sunglasses, without sunscreen, and no contact lenses or prescription glasses, because they also block out some of the UV rays. So it's just like you build a callus on your hands. So here's a little rave, I'll just read that from one of our favorite guys, Zaid Dahaj. Sunburn is not proof that sunlight is inherently dangerous. Sunburn is proof that you're underprepared for sunlight exposure, because you work indoors most of the time. You never get morning sunlight. You wear sunglasses that blunt POMC, it's a hormone precursor, activation and the creation of melanin. You slather on sunscreen, which alters the light spectrum to your skin in harmful ways. And you have a bright artificial light environment at night. Then you go to the beach and get roasted, only to blame the sun That's like blaming gravity after jumping off the roof. Okay, cells in light. This is the really hard scientific part, but we'll see how we do. Okay, so our cells are an amazing thing that there's not much known about. They are really, really small. You can't really get a good camera inside of them, although there are some electron micro photographs that are trying to get there. So how we even study cells is a whole art in and of itself. So inside of a cell is a watery environment cram-packed with all kinds of molecules and chemicals. There's mitochondria in there. But let's see, I'm really gonna try to make this work. Okay, speaking of Gerald Pollack, students in his lab discovered that light structures water. They were working on studying water in a microscope, and someone had shone a light into it, and they discovered that this area of very structured and highly latticed water appeared when different colors of light were shown into the water. So they were all fascinated, and they tried out many different colors of light, and they found that the infrared rays of light expanded that the most. So structured water is also called the fourth phase of water, also called exclusion zone water. So ice is solid, water's liquid, water vapor is gaseous, but this fourth phase of water, I keep pressing the wrong thing. The fourth phase of water, it's kind of a gel-like substance, but it is like a semi-crystalline gel, and it compacts the water into a much more structured shape. So see how it almost turns into a little lattice work. When that happens, there's a lot of science to this, but when that happens, it separates out positive and negative charges, which is basically how a battery works. So it's turning your cells into a battery that have a stronger electrical charge, and that means they have potential energy, and they can do more work. So that's a good thing in the cell. So structured water transmits signals more efficiently than kind of more loose water, also called bulk water in the cells. So the signals can be transmitted from proteins to other molecules. Signaling goes on from the cell membrane to the interior, and from the interior to the membrane, which is how substances in your bloodstream get into the cell and are emitted from the cell. There's communication from the mitochondria in the cell, those are the energy producing organelles, to the cell nucleus. The nucleus also transmits messages to the mitochondria. So there's all this signaling going on inside of the cell. So the more structured your water is, the more efficiently these signals can zip through. So, also, tightly structured water purifies your cell water because it keeps unwanted molecules out of there. So big molecules can't fit in between these spaces. Structured water also facilitates protein folding, which is a big thing in health. One thing, Sarah Pugh is one of our authorities that we consulted. She points out, she studied protein folding for 12 years, and she's like, there's no way it can happen as well as it does unless there was a quantum biology effect involved. So those of you into quantum biology, this is good food for thought, but we're not going to go into that today. So the whole cell benefits from this structured water, and the structured water is most strongly created when it's exposed to infrared wavelengths of light. The same thing also happens inside the mitochondria. Mitochondria is really, really small compared to the large cell. So it's getting down to molecular sizes. So we found that red and near infrared light dramatically increases the amount of ATP that the mitochondria produces. So one of the principles of all of this is when you compress the cell water or you compress the mitochondria, even a little bit, it really drastically increases the efficiency of the cell signaling even more than you would expect. I think one scientist said even 1 angstrom, which is like a 10 trillionth of a meter, if those little parts of the mitochondria get even the tiniest bit closer together, that the efficiency of ATP production increases by 10 times. All right, Michael?